nice to have that. A refurbished university building. It looked as ugly as this one. We don't see much of it. We are now in this building for 17 years. We have the computers on the 3rd floor and on the 4th floor. That is accidentally because it's just a reused building and the office is on ground floor. We will get that now. And 1st and 2nd for the offices, 3rd and 4th for the machine. So DKRZ has a mission. The mission is to be partner of climate science. We don't conduct science ourselves. So the mission is to have a maximum compute performance for our users, to have a sophisticated data management, and to have competent service. And integrated into the data management is, of course, all the hardware that we have, all the hardware resources, including, of course, the HSM system. So the vision is to reliably unlock the potential of the accelerating technological progress for climate research. DKRZ was founded already almost 40 years ago in '87, so next year will be 40th anniversary. And it was founded by a person who is a Nobel Prize winner, Professor Hasselmann, Nobel Prize for climate research. He was the first scientific director. We are operated as a limited non-profit company, which is a little bit special in Germany. It came out of the consideration that the question was, it was a compute center between the university and Max Planck, and the question was where to put the money. So they said, okay, we need a legal unit to have that. And so that's the reason why we are operated as a company. We have, as a consequence, 4 shareholders. The biggest one is the Max Planck Society with 55%, and the city of Hamburg, 27%, and then 2 smaller institutes that belong to the Helmholtz research community inside Germany. Alfred Wegener Institute, Bremerhaven, and Heriot, neighboring here also Geesthacht. Currently we have something like 100 people staff, and I have also a position as a professor at the university for high performance computing, and my focus is on storage systems. So file system things, also energy efficiency, but we did a lot with file systems in particular. The financial contribution might be interesting for you to know. So we get regularly money from part of our shareholders, from the Helmholtz community, not from these 2 particular institutes, but from the community itself, then from Max Planck, and from the city of Hamburg. So usually we get 45 million, and we get it every 5-6 years. We are currently in the status of having a procurement running for the HPC system, and then we'll also do procurement for refurbishment of the building, things like that. And HSM was part of the HSM that we now have, was part of it, but that contract was already done in last December, I think. Operational expenditures are covered by the shareholders. So the resource distribution is as follows. We are also a national center. We provide cycles for all of Germany, for all the climate researchers inside Germany. And the distribution of the resources is that 50% of the resources, that means CPU cycles and petabyte and so, go to the shareholders according to their share, and the other 50% go to the German-wide community. And we have a scientific steering committee. You can apply for compute time or data storage. So DKRZ is embedded into kind of an ecosystem here inside Hamburg that exists for many decades, where the people concentrate on climate research for a very long time. So Hasselmann and his people did that in the 70s already. So the things that he received the Nobel Prize for in 2021, these things were published in the 70s, I think. So there's a long history on that, and as a consequence, all these institutes are also located here in Hamburg, or most of them. So you see we have the Max Planck Institute neighboring, more or less neighboring DKRZ, and then a new building for the university where they are about to move into it in the next time. So we are cooperating with other players here in Hamburg. For example, there's a unit for how do I say that, hydrography and sea Schifffahrt, so for ship issues, whatever. Also climate things, but related to ocean and rivers, of course. And then other institutions, also the university has the Center of Excellence for its researchers, and there's a strong cooperation with these groups here. But they are all users, and we help them with the with running the code on our computer. So we do not conduct climate research. There is a little bit of research in the field of computer science, of course, coming from my person. And we have another person who is more into AI, so we do some things over there. But the climate research is conducted with our users. And so we provide Germany with our support, and that goes from the very south, from Garmisch-Partenkirchen, there are some institutes, up to Kiel, and oh, that is cut off. There's something in Flensburg also at the border to Denmark. And basically we operate in a mode that is more like a cloud provider. No? So everybody just gets cycles on our center, and then they usually store the data inside our center, because the volumes of data, they are enormous. It would be too complicated to transport them via network to the individual locations of the researchers. Instead, everything is kept at DKRZ, so they do the post-processing also at DKRZ, and also, let's say, the production of small films, animations, whatever. And only these smaller final products are eventually transferred over network to the site of the researchers. And that is the reason why we have this enormous capacity for storing data as well on the file system as on the tape. And of course, we need a powerful HSM between them. So this is a little bit of a history, what DKRZ has as machines in the past decades. It started off with a machine that had only one processor, a CDC 205 in 85 and before DKRZ was founded. That one had the performance of a cheap iPhone, of the first one. So at that time, 85, 86, the whole German climate research community conducted its research on a device that you now have in your pocket, battery driven. And that was room filling with 150 kilowatts, something like that. Then we had several generations of installations, NEC, Cray, and then we have an IBM, and now we have already the second installation from Bull, Athos, Eviden, whatever. They sometimes change, you know, the name. So that is our ranking inside the top 500 list. You see that in the past, that started only in 93, but DKRZ started with the machine in 88. So the first part is missing, of course, in the top 500. Whenever we got a new machine, we entered the top 500 list in a rank with 2 digits, so 54, 33, something like that. And then in the past, you might remember that, everything was moving quickly with respect to performance, so we fell off the list after 2 or 3 years, and then we bought a new machine and came back. But now with the last generation, and already with this generation, there is no longer falling off the list, because everything is so slow, everything slowed so much down with the development of aggregated performance that you see here. This is a view to our computer room. The light is switched off. Instead, we only have this decorative lights by Athos. 2 rows with racks, water-cooled, and I will give you some details on the next slide. We are currently on rank 163 in the top 500, but it moves down very, very slowly. Usually in the past, it doubled the rank. So when you had 163 in one list, that is the November list, then you had to think that not today or now, these days, you would double and be in the rank of 300, and next half year you fall off the list. But that changed dramatically. So the machine is composed of mainly CPU systems, and then also a few GPU. GPU at the moment is mostly used for either development of AI applications or for one already well-adapted application, which is the ICON climate and weather code. That is basically the only powerful code that is capable to run on GPU. Yeah? And that is provided by the Max Planck people. They run that on our GPU cluster. They also now have an own cluster purchased, so they can run their code on the GPUs. All the other researchers usually run on CPU, and within the Athos machine, we have around something like about 3,000 nodes, 370,000 cores, and 14 petaflop of performance. That is how this space between the racks looks like. So DKRZ used to have, and has here too, a powerful file system. So that is a Lustre file system that has more than 130 petabyte of capacity. Now I think we use it up to 80 or something like that, so it's filling up by the time. That was a tradition that DKRZ that, let's say, compared to what you see with computational performance. So inside Germany, well, I didn't look it up, maybe we are on rank 6, 7, 8, something like that. Compared to the other sides, and if you make the ratio to computational performance, I think we have about at least 10 times more storage than the other centers have. And there are a few reasons for that. The climate scientists at first produce huge amounts of data with each single run. And then also they want to keep the data for decades, because they want to come back to the data. And then they put the data on tape. I don't know whether they ever come back to it, but well, it's on tape then. And the tape fills up too, and the disk system fills up too. But we provide them with these means. And this is different to other sciences. I think they throw away more of the data that they produce, but if they had the resources as DKRZ provides, maybe they would keep more. It's just what you give to them. If Jülich provides the customers with something that is, let's say, comparable to the size that we have here, but it's 50 times more computational performance, but just with the size of our I/O system, it's up to their customers to say, okay, it's not enough. But I think for some of the sciences, that's okay. For climate science, which is data intensive and want to store it for a long period of time, that would not be okay. As the backend, we have a tape library. So we have up to 70,000 slots for tapes. We now do an installation of, this is a storage tech, so we will have a new one being operational fully in the next time. There's a shift between these tools, and then there will be, of course, a copying of tapes and things like that. Currently, we have 254 petabyte on tape around that. And the increase rate per year is in the range of 30 petabyte. So usually we buy Euro pallets with boxes of tapes, and then you need a person who puts them into the library. So that's a big one. I think that brings us to a very high rank with respect to storage sites for scientific data. Of course, there are other sites with, let's say, Amazon, whatever, Facebook, that have social media data and have huge amounts of volume. But for scientific data, we are in the leading ranks here. And obviously, we need a powerful HSM to move between the tape and the disk system. And Carsten will speak about that. So we have 5 applications. Now 2 of them will be merged. One department is the Department for Application that Hendrik Bockelmann is leading. He's also in charge of the procurement that we do. In their department, they help the people with the code. So usually the coding is left to the researchers. Then they come to us with the code. We help them with debugging, running it efficiently, taking care of the data volumes and things like that. Then we have 2 departments that deal with data management and data analysis. Here also going a little bit into the direction of AI, of course. Here doing these things like curation of the data, providing it via web front and to the community, things like that. So for this department, we have something like 30 plus staff, and the 2 of them, the new head is Christopher Cardo, also have more than 30 people in that, which is about to be merged department. And then systems department from Carsten, something like 15 people plus. They take care usually of the non-high performance hardware. So the high performance hardware itself, like the computer, that is serviced and maintained by Atos, by Bull. So we have contracts for that, and then obviously you have some administration in a center like ours. A few final words on climate research. So when you do these things, then the question is, how is everything interconnected? The researchers want to find out how this system of bringing in energy from outer space to Earth and then transporting it back, how that system works, to compute what the balance of it is, because the energy that remains on Earth is just that heats it up, obviously. So you have the energy that comes from outside, And then you have many factors, components in the climate system on Earth that are interdependent and that interact with each other. Important are clouds, because with more clouds you have less energy coming in, but also less energy going out, things like that. Then you have sea ice and land ice, very important components. You have the sea level rise and these things that come out from the land ice. And then you have singular events like volcano explosions that bring, for example, dust into the atmosphere, making it dark, and then it might have a cooling effect, for example. And then also you have ocean currents, but pretty complicated to compute, and you have human activities. And usually I add to the human activities things like DKRZ, yeah, because, but this is now a ridiculous effect for us because we have something like 2 megawatt, and you know the announcements of the AI people when they want to have 200 or 2 gigawatt. Yeah, so this is a hybrid that is not reflected in the HPC systems. But of course, I always put that here because we put a lot of effort into energy efficiency. So the current machine has this hot liquid cooling. We have a heat reuse in the neighboring buildings. The ugly building that you saw on the right side here of our building is a laboratory building, and it is good to transport heat to a laboratory because they have legal regulations to replace the air frequently in the building. Yeah? So you can heat it up frequently, that is good. So they can use our energy at least in the cooler times of the year, which is approximately in Hamburg 11 months out of 12. So. I'm from the south, so it's a bit, it's now very good, huh? But it's not so frequent. Okay, this is how everything is integrated. And then if you want to do the computation, usually you put a grid around the globe. You do that in 3 dimensions, have X, Y, and Z dimension, and do a discretization of the formulas that govern these laws of nature here in individual cells, and then compute for the grid cells the values. And you do this for a long time, and this is why you get this huge amount of output data out of our applications. So if you do the IPCC computations, that is for this climate report that is usually communicated to the public, then the grid distance is more in the range of 100 kilometers. But if you would want to do something like cloud and precipitation computation, you must have a grid that is more in the range of 1 kilometer, or a little bit less, let's say 500 meters. And the idea is, of course, that when you go down from a grid size X to a grid size X half, then you divide X, you have 2 times the points in X direction, 2 times the point in Y direction. You have to have more points in Z direction, and you have to have a shorter time step. Otherwise, the numerics will not work. And that usually means that if you want to divide it by 2, the grid distance here, that you have to have something like 16 times the computational performance to be able to compute that. And that is, of course, as you all know, 16 times the computing performance. We had that 15 years ago. That was easy. So the first procurement that I did here on my own was a factor of 20, going from the IBM to the first Atos machine. And then from first Atos machine to the next Atos machine, that was in the range of a factor of 3.5. And now from the Atos machine to whatever, we are more in the range of 0.5, 0.7, we will see. Yeah, it's not so nice at the moment. And I mean, you all know the increase in price, in particular with storage, that is a problem. Yeah, so this is how it is done. And if you do these things, what, let's say, the bleeding edge of climate research currently is this computation of clouds and precipitation, at least with respect to influence on climate change, then you can do that on our computer, but you cannot do these things that the researchers would like to do, which is to compute it for a simulated time of 100 years, or at least, let's say, 75 until the end of this century. Yeah, this is not possible. I will just now show you a small film that is produced with these precipitation computation, cloud computation, but it is only for, let's say, 2 weeks, 3 weeks, or something like that. So let's see whether this starts. Could someone press? Yeah, I don't know. Maybe you have to go with the cursor. No. To go with the cursor, the bar is, thank you, on the left. Thanks, great. Yeah, thank you. So this is a computation with precipitation and cloud development, which looks very much like a satellite film, but it's not. This has 21 million cells per level, and I think 100 levels in set direction, 150 or something like that. And it's 5 kilometers per cell. We do have other computations that have only a cell distance, a cell space of 1 kilometer. And it looks like a real film. It's really fantastic. But with our machine, you cannot do these long-lasting simulations for let's say, 100 years or 75 years. And then using this code here, this is computed with the icon code, closes more or less also the gap between weather prediction and climate projection, because that is then, this is the same physics in the end that governs the system, but that is then both in one, so to say, but currently there are not the powerful computers available to do that. Our customers are able to run that code efficiently in Jülich, but I cannot store the result there. Unfortunately. I don't know what Jülich is doing with respect to procurements. Okay, so that is what I wanted to say about DKRZ. Do you have any questions?
Are you trying for researching also based on quantum computing in this area?
We had a workshop a little bit more than a year ago about that, and had some specialists with us and discussed these things, and we observed the field. The exciting point is, of course, the following. This here has a mathematics of partial differential equations. Extremely complicated in quantum computing. There are many people working on it, and sometimes they say there are results, but I mean, I cannot judge it. I don't see it, but I don't understand the details, to say the truth. And then there are people, and then the AI people, they do these statistical things. And we look also into these things like discrete optimization, where there are already some success stories with quantum computing. So we think that there will be a connection between quantum computing and, let's say, the more traditional HPC in the next few years. We will keep our eyes open, but having then the quantum computer as a co-processor for this machine. And I mean, the completely undiscussed question at the moment is the question, how much does it cost? How much energy will it burn? And what's the procurement price?
The point is, quantum computing as its native does use less power, but you need to redesign from bits to quantum computers. So
right.
It's not just run it, you need to redesign it to use it natively.
Yeah.
And the good thing is, I was working on a company doing some simulations, quantum simulations. So even if you do simulated through AI algorithms, it's consuming less power than regular AI. The same thing.
Oh yeah, okay, yeah.
So you can improve performance and save energy when you move for some applications from classical AI to quantum AI.
Yeah.
Simulated quantum AI. And as you are talking using A100, there is a major improvement to the newer generations of NVIDIA.
Of course.
So
yeah.
When you use simulated, NVIDIA itself is providing the quantum runtime environment.
Mm-hmm.
We can develop today, and nowadays we did it
Yeah.
using the NVIDIA provided quantum AI algorithms. And this is really an important thing because quantum, a complete quantum field, is engineered and researched in Europe. So it's our own expertise.
Right.
And there are a lot of companies on the market who are doing both. One of the major ones is Quantum. They are entering now in NASDAQ, not in Europe.
Yeah.
So we are exporting our development to external companies.
Yeah. So yeah, that is true. We are observing the field and
really, I guess it would be interesting, especially for those high performance and high load applications.
Mm-hmm. Yeah. We
We
just did a procurement now, or we are about to finish it. So there's no quantum integrated at the moment. The next one will be in 6 years or so. And I think we might be seeing it already then.
I guess there will happen a lot of things in the next year.
Yeah. Yeah. Hmm? Further questions? There is no calculation for that at the moment. We will do that, I think, in the close future. The point is that if you integrate AI in a neighboring discipline like weather prediction, then the things are very easy because you make the prediction, then you have the satellite photo, you compare the prediction to the satellite photo, and then you improve the network. But with a climate simulation where climate is defined as a 30 years average, statistic averaging of what's going on weather-wise, you just do not have this ground truth. So they need to integrate it in a different way. They do that, but it's a little bit too early to calculate what kind of speed up that will bring. For example, with speaking about weather prediction, I can tell you that ECMWF published, I think, beginning of this year, something where they said, a press release where they said they can do it now with 1,000th of the energy. And that means they also would need only 1,000th of the machine. German Weather Service already got contacted by the ministry, where the ministry said, oh, we heard you don't need such a big machine anymore. And when the German Weather Service said, no, we are not that far yet. But of course, yeah, I made a talk about that. You can do this prediction step in weather prediction. There are two more or less equal numerical problems in it. The prediction step, which is one of it, you can now do on a powerful desktop computer. You don't need a supercomputer anymore with AI. And usually the weather report is better than the one that is based on physics. They don't know exactly why, because the AI is trained on historical data. So let's say extreme weather are not so well represented in the past as they might show up in the future. Nevertheless, the AI weather prediction is usually more powerful. Hurricane trajectories, for example, are better. Extreme weather predictions are better. So it's a really cool field, but unfortunately we do climate only. So we have to find other ways how to integrate that.